Okay, today we are going to discuss about the induction motors, how the induction motors are designed, and what are the considerations or parameters we should meet to design a induction motors. Okay, first is let us first start with the construction details of induction motors. So this is a figure which shows the basic construction of the induction motors. Here we can see basically two different parts, mainly the stator and the rotor. And while designing a three-phase induction motors, the most important parameters which we need to consider are the main dimensions of the motor, like the diameter and length of the core. Then comes the stator design part, then comes the rotor design part. So these are basically the main important portions to be studied or considered while designing a three-phase induction motor. Now let us just have a brief introduction about the induction motors. What is an induction motors? Then what is the constructional details of an induction motors, and how an induction motor can be designed, and what is the output equation of induction motors. Okay, induction motors are the AC motors which are widely used in industries. In most of the industrial applications, these type of induction motors are widely used, that is from small workshops to very large industries. Okay, these are employed in applications such as centrifugal pumps, conveyors, compressors, crushers, drilling machines, lifts, etc. So these kind of AC motors are universally used motors. And going to the construction details of this induction motor, it basically consists of two parts. One is the stationary part, which is called the stator, and the rotational part, which is called the rotor. Okay, now the difference between an induction motor and a DC machine is in the following aspects, that is the laminated core, then absence of commutators, then uniform and small air gap, and practically almost constant speed. And this is how an induction motor differs from a DC machine. Okay, as I have already told, there are two basic parts, the stationary part or stator, rotating part, and rotor. So the stator consists of, what do you mean by what is the stator part? The stator consists of basically a three-phase winding, which is usually an insulated copper or aluminum winding to carry the current. Then there is a magnetic part, which is usually made from laminated silicon steel, which is used to carry the magnetic flux. Okay, now the stator means it is an outer stationary part of the motor. The outer stationary part means the outer cylindrical frame of the motor or yoke, which is usually made up of a welded sheet steel, cast iron or cast aluminum alloy. There is a magnetic path also, which comprises a set of slotted steel laminations called a stator core pressed into the cylindrical space inside the outer frame. Here you can see the core part, outer frame, and there is a stator core part you can see in the uh, outer portion of the motor. Okay, now as I have already told, the stator have stator slots in the stator core, and in these stator slots there is a three phase winding or insulated electrical three phase winding is placed. Okay, so based on the power rating of the motor or based on the specifications required, this cross sectional area of these windings must be large enough. Okay, now moving on to the rotor part, the figure shows the stator and rotor laminations. As you can see, there are stator core and the slots are placed on the stator, and in this and the stator is made up of laminations, and after a small air gap inside you can see a rotor, and rotor have a rotor core, and it is also made up of silicon steel laminations, and the rotor also is comprised of slots where the conductors are placed. Now moving on to the rotor, let us discuss about rotor. This rotor is basically the rotating part of an induction motor. It consists of slotted silicon steel laminations pressed together to form a cylindrical magnetic circuit or and electrical circuit. Okay, based on the type of rotors, the induction motors are classified into two types. They are squirrel cage induction motors and slip ring or wound rotors induction motors. Okay, Now, squirrel cage rotor means it consists of there are various loads which are on the rotor core, and in these loads, a set of aluminum or copper bars are placed, and these bars are connected to an end ring at each end of the rotor, or in other words we can say these windings or copper bars or conductors are short circuited by means of end rings at either end of the rotor. Now coming to the wound rotor means the rotor have rotor slots, and in these slots a winding is placed, insulated three phase winding is placed, usually star connected windings are placed. Okay, and these windings are taken out to three slip rings mounted on the end of the shaft. And another important advantage of the slip ring induction motor is that a three phase rheostat can be connected to the rotor circuit through the slip rings mounted on the rotor shaft. In this way, we can control or we can vary the resistance of the rotor. Okay, these are the construction details of different parts of induction motors. So, the figure number 2, it shows the stator laminations. Then figure number 3, it shows a stator core with a smooth yoke, then a stator with a nibbed yoke and a squirrel cage rotor. In the squirrel cage rotor type, you can see there are various loads on the stator core, laminated stator core. Okay, in these slots, their skewed slots are placed, and in these slots, the copper bars or aluminum bars are placed, and they are short circuited at the either end through the end rings. Now, the next figure is the slip ring rotor. You can see in the slip ring rotor also slots are placed on the rotor, and in these slots a three phase winding is placed, and these windings are wounded as shown on the figure, and the windings are taken out through slip rings mounted on the rotor shaft. Okay, so these are the construction details of induction motors. Now, coming on the working principle, I just briefly explained. We have already learned in the previous semesters the working principle of induction motors, how an induction motor works. Okay, an induction motor, as I already said, a stator and rotor is there. The stator have a three-phase winding, and a three-phase supply is provided through this stator three-phase winding. When a three-phase supply is provided to the stator winding, a rotating magnetic field is produced which rotates at a synchronous speed, which is Ns is equal to 120 F by P. This synchronously rotating magnetic field, it sweeps past the air gap and it cuts the rotor conductors placed on the stationary rotor. Okay. Now, since the conductors are cut by the rotating magnetic field or magnetic flux, EMFs will be induced in the rotor conductors by Faraday's law. So, since the EMFs are induced in the rotor conductors and they are short circuited conductors, rotor current will flow, and because of this rotor current, a torque will be developed. By Lenz's law, it opposes the cause producing the induced EMF or induced current. And here, the cause which produces this induced EMF is the rotating magnetic stator magnetic field. So, what happens is the rotor rotates by Lenz's law, the rotor rotates due to the torque produced. It will always rotate at a speed which is less than the synchronous speed, which is called capital N, or the rotor speed. This is because if it rotates the synchronous speed, there will not be any mutual induction, or there will not be any EMFs induced in the conductors, and hence there will be no torque produced. Because of this, the rotor always rotates at a speed less than the synchronous speed, which is called, another word is there, slip speed, which is called slip. Percentage slip s is equal to ns minus n by ns into 100, or slip speed n is slip speed is ns minus n. Okay, so this is how the induction motor rotates. Now, coming to the design part of induction motors, as I have already discussed, while designing an induction motor, the important considerations or parameters need to be met are: first one, the main dimensions of the stator, that is the D, a capital D and capital L, that is the diameter of the stator, and then the core length. Now, coming to the next part is the stator windings. So, stator windings means what kind of windings are used, or what kind of connections are used, number of stator slots, how many stator slots are required, and what is the area of cross section of the conductors placed in the stator slots, etc. These are some of the, or what is the current through the stator conductors. These are the considerations while designing a stator winding. Next part is the designing of the rotor part or rotor circuit. Rotor circuit means, as I already discussed in slip ring motors, we have rotor windings, three-phase windings placed. So what we have to design is what is the number of rotor slots, what are the total number of conductors to be placed in the stator slots, what is the current carrying in the rotor conductors, etc. Now later it comes to the performance characteristics. Okay. Now we will discuss the output equation of induction motors. What is the output equation of induction motor? What is an output equation? Output equation means it is a mathematical expression which gives the relation between the various physical and electrical parameters of the electrical machine. So this is very important while considering the design of motors. Let us consider an M-phase machine. Let the output Q in kW is represented in kW.